Let's say it's 300 BCE and you want to build a fence around the wooden shack that is your home. You have 500 feet of fencing material and you're building this next to a river, so one side of the enclosed area doesn't need any fencing. You want to find the dimensions of the field that will enclose the largest amount of area, or in other words, you want to optimize the area. Anytime we're dealing with optimization problems, you need two functions that are related to each other. Since we're given the amount of material and want to maximize area, we should use the perimeter and area functions. We'll call the area function our optimizing function and the perimeter function the constraint function. So our area function is given by the area is equal to x times y, and our perimeter function is given by the perimeter is equal to x plus 2y. Since we have 500 feet of fencing, we can plug in 500 for p. Now, we want to rearrange the function to solve for either x or y, and it doesn't really make a difference which one you choose. So I'll go ahead and solve for x and get x is equal to 500 minus 2y. Now that we have a value for x, we can plug that into the x in our area function. Now that we have the area expressed in terms of only one variable, we can take the derivative and find the global maximum. Our goal is to maximize the area of our fencing, which is just another way of saying we want to find the values of x and y for which the area is the greatest possible value. So we set the function equal to 0 and find the y value, which tells us the critical point of our area function. At this point, we always have to check to see if our value is a local maximum or minimum, which we can do by simply analyzing how our derivative function behaves at values less than or greater than 125. In our case, the derivative is positive for values less than 125 and negative for values greater than 125. To visualize the behavior of the derivative, take note of the awkwardly drawn curve corresponding to the slope of our area function. Whenever the derivative changes from positive to negative at our critical point, we have found a local maximum. And since our area equation is a convex parabola, meaning it opens downwards, we know that our critical point will be the global maximum of the function. So we now have our y value and we're ready to solve for the x value. We do this by plugging in the y value to the perimeter equation, which we already arranged to solve for x. Plugging in 125 for y, we find that our x value is equal to 250. With both the x and the y value solved, we simply plug them into the area function to find the maximum possible area using the 500 feet of fencing we started with. What we get is that the area is equal to 125 times 250 for a total area of 31,250 square feet. So to recap, first we draw a picture of our problem to help us organize the variables. Then we look for two functions that are related to each other by their variables and identify which of the two we need to optimize. We then take the constraint function, or the one that isn't being optimized, and we solve for one of our two variables using the given initial condition. In our case, it was the 500 feet of fencing. We plug that value back into the optimizing equation and then take its derivative to find the critical point. We check to see that the critical point is in fact a maxima and then use it to find our missing variable.